our second speaker gets set up here. Our second paper is also in the visible light communications realm, but now we're looking at V2X. That's our vehicle-to-vehicle, vehicle-to-infrastructure, vehicle-to-anything, vehicle-to-X communications. And we're also kind of on top of this really exciting area around neuromorphic cameras that are having just an absolute explosion right now. So I'm pretty excited to see these things come together. Our presenter is Kenyu Xu, who's a third-year PhD student in the School of Computer Science at Peking University in China. His advisor is Professor Chenren Zhu. Kenyu's research interests include wireless networking and visible light backscatter communication. This might make sense for what his paper is about. Recently, he's also been working on acoustic sensing and metasurfaces as a research intern at MSR Asia. And I almost dragged that out long enough, and I think I'll just let him get finished and then get started right now.
Okay, so can you hear me? Okay. And good afternoon, everyone. I'm Kenyu Xu from Peking University. Today, I'm going to introduce our recent work when visible light backscatter communication meets neuromorphic cameras in V2X. This work is in collaboration with my coworkers in Peking University. Okay, so our story starts from intelligent transportation systems. We all know that the transportation system used to be bare metals on wheels, but now the system has been embedded with hundreds of or even thousands of sensors and embedded computers to build the intelligent transportation system. The intelligent transportation systems are envisioned to assist self-driving cars and alleviate traffic congestion and air pollution, and also enhance traffic safety. So one key technology for intelligent transportation systems is vehicle-to-everything communication systems. The vehicles and the road infrastructure, together with every object on the road, should be connected and to build the vehicle-to-everything communications. So far, the vehicle-to-everything communications are based on RF technologies such as DSRC or cellular V2X. But so far, they are not widely deployed yet. So how can we build everywhere to a real-world deployable vehicle-to-everything communication system? We find the chance might lies in the visible light. We have visible light everywhere on the road, so we believe the everywhere visible light can be a promising medium for V2X communications. As mentioned in the last presentation, there are already many visible light communication systems, mostly in indoor scenarios. And for V2X outdoor scenarios, we may use the lighting infrastructure, such as traffic lights and headlamps, to be the transmitter of visible light communication, and use some cameras or photodiodes as receivers. That's quite the same, but the challenge lies in the outdoor optical channel. It's very complex. It has many noise, interference, and reflections. So such interferences may be the most important and the most different thing for outdoor V2X scenarios. And we identify one bottleneck is the receiver of the VLC. We want to answer, are the current existing optical receivers competent for VLC V2X? To answer these questions, we first identify three practical requirements for VLC V2X. The first is high sampling rate. The receiver should be a very high sampling rate to ensure the overall data throughput. And the second is spatial resolution, because we want to exclude the ambient optical noise. And the third requirement is dynamic range. We want the dynamic range to be as high as possible to handle the sudden lighting changes. So let's see the existing receivers of VLC. Most VLC systems currently use discrete photodiodes to be the optical receiver. It has a quite high sampling rate that is indeed adequate, but it has no imaging capabilities. It is easily interrupted by ambient noise, such as sunlight. Another type of receiver are cameras. they are everywhere in our daily life, such as smartphones or data recorders of the vehicles. It has a higher resolution and imaging capability, so we can easily detect the area of interest on the road to find the VLC transmitters. But it has a low sampling rate, only about 60 frames per second. That is 60 hertz. That is not sufficient for a practical on-road communication system. So it seems that the existing receivers are not competent for our VLC V2X scenarios. And is there any opportunities that we can make it better? We identify a new type of cameras named neuromorphic cameras. We believe this is the new opportunity for VLC V2X communication receivers. Maybe some of you have heard of event cameras or dynamic vision sensors, that is DVS. That is one type of neuromorphic camera. It only reports the changes in brightness and staying silent otherwise, and it's quite mature recently, and you can, there are a few commercial companies and you can buy it somewhere. But we want to say that the neuromorphic camera is actually more than DVS. There are more types of neuromorphic cameras, such as the NN vision sensor, ORAM vision sensor, and the spike camera that is going to introduce today. The spike camera is inspired by the sampling mechanism of primate fovea, and this is the camera we want to focus on in today's talk. So what exactly is a spike camera? Let's watch a video.
Introducing the spike camera. The spike camera has each pixel working independently to convert a set of photons to one digital bit, namely a spike. The interval between adjacent spikes indicates the light intensity. The spike stream collected by the spike camera portrays precisely the continuous process of light change, whereby the light intensity at any given instant can be calculated by inversion, thus realizing high-speed continuous imaging. Based on the same chip technology as conventional cameras, the spike camera has a speed 1,000 times faster and is able to record high-speed visual phenomena difficult to portray with conventional cameras. As conventional cameras cannot capture the information between adjacent exposures, spike cameras completely solve the time loss problem of conventional cameras.
Okay, now that we have introduced the spike camera, let's see the spike camera as a representative of neuromorphic cameras. Will they satisfy the requirements for VLC V2X receivers? First, for the sampling rate, the neuromorphic camera supports up to 40 kilohertz. That is a sufficient sampling rate for VLC receivers. From the resolution, it has 400 times 250 pixels in one frame, so we can also, it is also an adequate resolution for excluding ambient noise. And for the dynamic range scenario, it is also the an advantage of neuromorphic camera. It has a very high dynamic range. Therefore, in this work, we are going to explore when neuromorphic camera meets VLC, and our prototype is named Neuromorphic VLC. Let's briefly introduce the system architecture of our system. We first have a VLC transmitter, which can be embedded in the tail lights, headlights, or road lamps of the existing illumination infrastructure. And the vehicles can be equipped with cameras, that's the spike camera. The spike camera can be embedded into the existing devices, such as data recorders. The spike camera outputs and receives the spike streams. The spike streams are the output of spike cameras. And what we want to do is to extract the received, the modulated message from the spike streams. So we need a series of algorithms to process the spike streams. There we have a few challenges. The first challenge is the spike stream is actually a different representation of images. It is different from the intensity-based images as conventional cameras. Therefore, the existing camera-based algorithms cannot be directly applied. And the second challenge is the spike streams are quite noisy due to current hardware restrictions. So the noises should be specially handled and treated to ensure low bit error rates. Therefore, we come back to our system architecture, and our key contributions are the data processing pipeline to process the output of the spike camera. So when we are going to introduce the data processing pipeline, and the first process is image reconstruction. You have seen the videos, and we would like to mention that videos are recorded at 20 kilo frames per second, but played at 60 frames per second. So they are actually slow motion videos, much slower than in the real world. So for each pixel, we have a spike interval delta, and we compute the intensity of each pixel with delta over k, where k is the threshold for only focusing on the bright pixels. And we further apply a transformation kernel to further process the intensities. Now, with the image reconstruction algorithm, we can convert the spike streams to images that is more friendly to human eyes or conventional images. The next step is to quantize the image. We quantize the intensities for each pixel with the upper bound and lower bound over the few of a short duration of time, and with the threshold upper bound plus lower bound divided by 2. And as we can see, the quantization results are actually pretty good, because you can see in these areas they are quite united, but in the other areas they may be very noisy. So the next step is to denoising the quantization results. And to denoising the quantization results, we set the quantization result to 0. That is different from the 1 or -1 in the previous step. And if the lower and upper bound are too close to each other, that is, if the upper bound and the lower bound are too close, we believe it is not shining and it's ambient noise. So it's not the area of interest and should be excluded. So as we can see, the noise are much alleviated. And the next step is demodulation. Note that we have quantized the images, so there are only 2 values for in the areas of interest, and we can detect the packet with a pre-known header, that is a preamble. And we can demodulate the bits from the quantization results according to our coding schemes. And so far, the algorithms only deals with static scenarios. Actually, we only focus on the key points to demodulate the signals. That works properly when the tag or the devices are static. But if the devices are mobile, if the key point is moving outside, not the area of the interest, that would be a problem. So we further design a tracking algorithm to handle this problem by setting the signal qualities. We identify the signal quality are composed of 2 parts, that is luminance and similarity to nearby pixels. And we move the key point to a nearby point with the best signal quality to consistently tracking the pixel with the best signal quality. And we consistently use the key point for demodulation. And so we can update the key point. And here are our in-lab experiments. We mount the spike camera onto a cardboard and simulate this scenario. And as we can see, we also use the transmitter we use is actually a VLBC transmitter. What is VLBC? It is visible light backscatter communication. It's one type of visible light communication mechanism that features low power consumption and simplicity of design. The first result is data rate. Our system achieves up to 4.8 kilobits per second with near zero bit error rates. And we would like to mention that we are not transmit at 4.8 hertz. Actually, for each, for the transmitter, we only transmit at 100 bits per second, and we divide one transmitter to be 8 parts, and overall data rate is enhanced. For the mobility scenarios, we test a few moving scenarios, such as static, far, moving, and moving faster, and they all works properly. And for the turning and shaking, they are more complex and are not well handled with current algorithms. And for the distance, we use simulated scenario and scale down the image, and we find that for in the static scenarios, it supports up to 800 meters, and by mobiles, it will be more complex. And here are my conclusions and opportunities. We identify that neuromorphic camera is a powerful receiver for VLC, and it chimes with RF massive MIMO. The communication range is a great opportunity that requires further to be solved. And from communication to networking, the camera enables direct multiple access with separating different areas of interest in the FOV. And it further requires real-world deployment. And that's all for today's presentation. I'm very happy to take any questions.
Hi, thanks for the great talk. I'm Bhavna from UMass Amherst. So my question was, can it sense, like the camera can it sense multiple LEDs in a frame? If yes, is there a limiting number to how many it can sense simultaneously? Because that might help increasing data rates even further.
Okay, it is actually decided by the FOV of the camera. If the FOV and multiple tags can be separated with adequate pixels, and it can be separated, but in our current design, we only divide one tag to be 8 parts, and so that works properly in our experiments. We also conducted a few experiments and see that we can scale down the number of effective pixels by 8 times, and it still works in static scenarios. But for the moving scenarios, the tracking errors may occur, and so it will be more complex. So yeah, for your question, I would answer, yeah, for static scenarios, it's very easy to handle. But for mobile scenarios, things would be much more complex.
Thank you.
Thank you for your very interesting work. My name is Xiaohu Zhang from North Carolina University. So I'm consider, since light communication is greatly impacted by light condition, right?
Yes.
For example, your proposal is for vehicular communication. In case we have many vehicles, I mean, does it impact the different light source?
Yes.
So this is my question. Yeah.
Okay, actually, the current prototyping is one type of backscatter communication. So backscatter means it does not emit light, so it reflects the ambient light. So if the ambient light is stronger than itself, the transmitter itself is stronger transmitting signals. So the performance will be better, actually. And if you want to say that there may be more ambient noises in the real world, and that's the camera can work properly, because camera has the ability of imaging, and we can easily detect different areas of interest. If there are some areas that are not of our interest, we can easily exclude them with some image processing techniques.
Okay. So did you consider any, for example, adversary attacker? So sometimes Yeah, if you emit a different frequency of the light source.
Yeah,
how
that's
it
a
could
great
happen.
point. Yeah, it's true that security and privacy may be also challenging, maybe also very challenging for railroad, and it can be solved with some additional designs, such as, visible light features its line of sight, so you must see the attackers when he want to attack me, right? So that is a key point, that it is different from RF attackers.
Okay, thank you.
Thank our speaker one more time. All right, for our next speaker, get set up. Yeah, perfect, awesome. We have one more presentation in the light session, multi-camera lighting for mobile AR. We're moving away from VLC, interested in just understanding how lighting across multiple cameras could improve the performance